when the time comes.
Buenos dias. Hello, good morning, good afternoon, good evening, everybody, wherever you might be. It is my great pleasure to host today Marcelo LACA, who is now in Victoria, and I am in Santiago. So our North Atlantic seminar is actually West Pacific seminar today. But whatever the geography, the mathematics is universal, and we have a high temperature phase transition from number theory. Marcelo, it's all yours. Take it away.
Thank you, Piotr. Thank you very much for the invitation, and I appreciate the opportunity to talk at the North Atlantic Noncommutative Geometry Seminar. What I want to talk about today is a new paper joined with my student Tyler Schultz on a high temperature phase transition from number theory. I will try to explain at least the words in the title before I say what we actually did. So this has been an ongoing project for a long time. It started as a master's thesis, but it ballooned into something much bigger than that. So Tyler finished his master's and is now doing a PhD with me on similar topics. So, okay, so just in case, let me start with a, oops. Let me start with a definition here of what I mean by a C-star dynamical system. It is a C-star algebra A, and we assume it's unital in a one-parameter group of oromorphisms of A. So these are the Heisenberg picture for a quantum, for the evolution of a quantum system or C-star algebraic dynamical system. So for this model, the states are fixed and the observables evolve with time through this time evolution. So technically, the observables are the self-adjoint elements of A, and the time evolution is a continuous one-parameter group in the sense that for fixed A, the map that goes from a real number to sigma t of A is non-continuous. And then the states, as probably most of you know, but I repeat anyway, are linear functionals that are positive and have norm 1. And these things are not independent. If you have norm 1, then it's continuous. And when you read the state evaluated at sigma t of A, then you're supposed to interpret that this is the expected value of the observable A at time t when the system is in the state A. So that's just for general culture, because the next thing I'm going to do is define equilibrium states. And these are equilibrium in the sense of thermal equilibrium. You're supposed to have a system that is embedded in a very large so-called heat bath at constant temperature, and then you wait until the system reaches equilibrium. That thermal equilibrium is represented by a state. And states of thermal equilibrium are characterized by this KMS condition. So phi, a state of A is KMS beta state, where beta is the inverse temperature of this heat bath. If when you compute the state on the product AB, you get the same as you compute the state in the product of BA, except that A is affected by the oromorphism computed in imaginary time. And for this sigma I beta of A to make sense, then you need some special elements A, called analytic, and I'll tell you in a second what they are. So it's like a trace condition.
Sorry, may I have a question?
Go ahead.
You have written that there exists an entire function. I believe that this function should be analytic only in some strip, not necessarily on the whole complex plane. Am I right?
There is another version of the KMS condition where you seek an extension that interpolates the two boundary values at the real line and then at a constant imaginary line. And for that, there is what you say. But in general, if one restricts to analytic elements, for which there exists a function, so you restrict the elements, then the function is entire as an extension to the full complex plane.
Ah,
So
okay. Thank you.
the point is that you restrict the elements, but still. Let me go. I'll get to that in a minute, and I'll say a bit more. But so you interpret this KMS state as a tracial condition where it's not quite a trace, but it's a twisted trace by sigma computed along imaginary time, and that's just an algebraic condition. The meaning of sigma analytic is an element is sigma analytic if the function that goes from t to sigma t of a, that is assumed to be continuous, it is actually, it can be extended to an entire function for the whole complex plane. So what you were seeing in the previous slide, here this t goes to sigma t of a non-continuous, that is really the restriction of an entire function for a in a specific collection of analytic elements. But the point is that there are enough of those analytic elements in any C-star algebra with any dynamics to form a sigma invariant dense star subalgebra. So because of that, if you have a condition that is expressed in terms of analytic elements, really you're imposing a condition on the whole algebra because you're saying something about the states on a dense star subalgebra. So it is a fact that this KMS state for a fixed beta, 4-dimensional K is simplex, and that means that it is a compact convex set that is has this unique representation property for every point as an combination, generalized convex combination of extremal points. And if you look at the GNS representation of those extremal points in the KMS simplex, they are factors in the sense of von Neumann and Murray phenomenon. So their extremality is associated with factor. In the physical interpretation is associated with being a pure phase. So it's a homogeneous phase of equilibrium, of which there could be many at a single inverse temperature.
Sorry, just a stupid question. When you have these extreme points at which you have von Neumann factors, are these states called factor states?
I call them factor states, yes, I call them.
Okay.
Yeah.
Because I remember a long time ago I was working with such factor states.
Yeah, exactly. So the terminology may not be universal, but whenever I say something of a state that has a meaning for a representation, it is a GNS representation of the state that has that property. So we call them factor states, and that means that if you take the von Neumann algebra of the GNS representation, it's a von Neumann factor. Okay, so those are the models for thermal equilibrium, and there are lots of properties that are more equilibrium-like than this KMS condition. I don't have really time, or maybe I don't know enough to explain all of them, but once you start seeing the properties, you start believing more and more that this makes sense as a condition for equilibrium. Instead of going through all those properties, let me give you a few examples that maybe can help your intuition and maybe connect with things that are known. So the first example, or maybe the 0th example, is the finite quantum systems. And a finite quantum system, the C-star algebra is the n by n matrix. So fix n and take n by n matrices. And then when you take n by n matrices, all the dynamics, all the point non-continuous time one parameter group of holomorphisms, they're implemented by a Hamiltonian in this way here. So sigma t of a is the conjugation of a by e to the ith, e to the minus ith for some. And this Hamiltonian is not uniquely determined, but if you make it positive, this is the matrix, right? So it's a self-adjoint. If you make it positive by moving, adding a constant, so that the smallest eigenvalue is 0, then it's unique. So with this normalization of having a smallest eigenvalue equal to 0, then you can say that every time evolution comes from a unique Hamiltonian, positive with smallest eigenvalue 0. So that's the parametrization of all the dynamics by Hamiltonians. And the states of matrices are just the linear function of a matrix can be written down as trace with it's called a density matrix. So every state has a density matrix, so that the state applied to an element is equal to the trace of that element times the density matrix. And what density matrix means is a positive matrix of trace 1. So it's like the generalized probability distribution for matrices. And but generalizing from statistical mechanics, one can prove that there is a unique state, which is called the Gibbs state, that minimizes this formula here, which is called the free energy. So the free energy of a state is minus the trace of the density of the state times the log of the density of the state. Here you can see an entropy term. And then beta is a constant, this is the inverse temperature, times the trace of Q times the Hamiltonian. So the density times the Hamiltonian. Now, this is a fact that I bring from and I take as given, that the Gibbs state minimizes the free energy. And the density of that Gibbs state, or the Gibbs density, is this formula here. So is e to the minus beta h, that's a matrix, and then it's normalized so that the trace, divide by the trace, so now you have this normalization here is implemented by dividing by the trace of e to the minus beta h. So that equilibrium density is unique in the sense that it minimizes the corresponding state minimizes the free energy. So that's, let's say that's understood and it represents Gibbs equilibrium for this type of evolution, quantized finite system. But then there's a property that one can verify without too much problem if you know what you're trying to do. This density, Gibbs density, is a unique density matrix that satisfies this this middle equality. The trace of AB times the Gibbs density. Now here I've substituted a Gibbs density by its formula. But then I introduce on the right, first I use the trace property to bring this A over, and then I introduce this factor, which is 1, because e to the beta h times e to the minus beta h. But then this thing marked in blue here can be interpreted as sigma I beta of A. So if you now read this equality in terms of what it does to the state, then the Gibbs state of AB is equal to the Gibbs state of B sigma I beta of A. So because the density is related to the Hamiltonian, and therefore the dynamics in this way, the Gibbs state satisfies the KMS condition. So, and the uniqueness tells you that it really characterizes. So the KMS condition characterizes Gibbs states for the finite system. So with this example, I think we can see two things. We can see that some notion of equilibrium, or pre-existing notion of equilibrium as minimization of the free energy, turns into the KMS beta condition. And at the same time, how it turns into the KMS beta condition is because of the mix of density with Hamiltonian, or e to the minus beta times the Hamiltonian. They look the same. One is the density, the other one is the Hamiltonian, or the time evolution evaluated in imaginary time, and you can interpret it that way. So that's what happens for finite systems. Now I'm going to jump and give you another example that is a bit more complicated, but it has to do with by now long history of 30 years, of more than 30 years in fact, of quantum systems that arise from non-physical motivation, but from number theoretic motivation. And the ideas were introduced in the late 80s by independently actually by two mathematical physicists, Bernard Juliat and Donald Spector.
Sorry, before this example, could you go back to the previous slide? So I wanted to ask how much of this example still makes sense if we are in infinite dimensional setting? Since you only need e to the power minus beta h to be trace class, yes? Is it right?
Yes, which you can arrange usually by by taking beta larger. So as you take larger beta, you improve the terrestrial conditions. So yes, it will extend, not in general, because it will depend on the state, but when you represent it on the GNS representation of the state, this is often the case. And the next slide has an example of precisely that.
Okay, thank you.
So this Riemann gas was introduced by Julian Spector with the idea of using the notions of quantum statistical mechanics to interpret at least some number theoretic facts. And what they propose is to view prime numbers as elementary particles, so non-interacting bosonic so-called primons. And the quantization is some sort of Fock quantization in which for every prime p, you take an element mu p, which is an isometry, is a left creation operator of the particle p. And when you put it in a C-star algebra, it becomes a copy, this mu p, which is the isometry corresponding to the prime p, is a unit, an isometry, and it generates a copy of the C-star algebra of unilateral shift. So this is the usual, what we call Toeplitz algebra. This p is one for each prime, but all of them are isomorphic to each other because mu p is a universal isometry. Mm-hmm. And then for the dynamics, this they choose very carefully, the creation operator mu p is sent by the dynamics to p to the it mu p. I didn't write it down, but this is equivalent saying that the Hamiltonian has spectrum log p. So what they're choosing is an energy for each prime for a specific reason that will become clear in a moment. So this p to the it is really e to the log p it. And the Hamiltonian has eigenvalue log p. So when you put them all together, these primons, you put them together in some sort of bosonic way, which means you take the tensor product. So these are commuting copies of the C-star algebras of each of them. And this tensor product over all primes of the C-star algebra of mu p, on the one hand as a product, can be also seen as a C-star algebra of a semigroup, because this semigroup here, n cross, is the multiplicative semigroup of non-zero natural numbers. So by prime decomposition, you can factor every natural number as a product of prime powers, and each of the prime powers comes from the corresponding factor mu p. So that isomorphism of C-star algebra there is simply implemented at the level of C-star algebra by the prime.
Sorry, just a quick question, if I could.
Sure.
Is this tensor product uniquely defined? Is minimal or maximal, or it doesn't matter?
It's Toeplitz algebra, so it's all the same.
Even infinite?
Infinite, I don't know.
This is uniquely defined, yes.
Because you just label Toeplitz algebra by primes, and then you take the infinite tensor product, basically.
Yeah. So
okay.
For the dynamics, you do a non-interacting dynamics in which the dynamics on the tensor product corresponds to the tensor product of the dynamics for each factor.
Okay, there's a question here from the room.
Right. So may I ask how the mu p shifts are interpreted, like in terms of these particles? Are they like creation operators, something like that?
Yes. They are creation operators of each primon p.
Okay, so it's a creation operator. Like it basically shifts the amount of primons of that same p that are currently in the system, right? Something like that.
Yeah. And then if you create another p as a mu p squared, etc., etc. So.
Right. Okay. Perfect.
So, okay, so the dynamics is, as Adam was asking, is implemented by a Hamiltonian in the representation on L2 of n cross. So this sister algebra of n cross has a natural action. In fact, the definition is as a sister algebra of operator in L2 and of n cross. And on that spatial representation of the sister algebra, there's a Hamiltonian which has diagonal eigenvalues n to the minus beta. It comes from this p to the it. This should be logarithm. It's a logarithm missing here. Oops. Should be log n. Okay, I'm confused now. Okay, maybe I should say that.
But I will not change anything.
Maybe that's oops.
But he's just checking his calculation.
Anyway, there's a bit of a disconnect in my slide here, but the dynamics is implemented by Hamiltonian. I think I got the wrong eigenvalues of the Hamiltonian here.
Okay.
But the point is that for each, and this you can compute, I didn't do the computation, but you can compute that a Toeplitz algebra with this dynamic has a unique equilibrium state. It's not a hard computation. It goes directly from the definition of the KMS state. And since for each factor there is a unique equilibrium, then in the tensor product there is a unique equilibrium. And it's the tensor product of states for each of the factors. So in the region of convergence of the zeta function, that's what it is a zeta function. For beta bigger than 1, there is a density, there's a Gibbs density, which is a trace class operator, e to the minus beta h, normalized, that it has trace 1. And that Gibbs density is a spatial representation of the state, or in the representation on L2 of n cross, the Gibbs density is the density of the unique equilibrium state, the unique MS beta state of C star of n cross of the whole system. And this factor that is needed for the normalization, of course, has to be finite, but it is equal to the Riemann zeta function. So compute that beta.
So Marcelo,
this line here is correct. Maybe that one there wasn't so correct, but this one is correct here.
it looks to me like your trace function and the eigenvalues of the Hamiltonian, they're pretty much compatible. So I would argue that everything is correct.
You think I got this one right? I mean, I'm not sure.
Yeah.
Oh no, okay. This one here is correct. You see, it's e to the minus beta h that is minus beta and n beta. So there should be this h is e to the minus beta h.
There should be logarithm of n, then it will be correct.
Yeah, you
So
can put
h
log
is
n
the
here.
diagonal matrix with logarithm n as eigenvalues. Yeah.
Maybe I can. All right. So this is a suspect there.
Okay.
Okay, so okay. Oops. Okay, so this Riemann gas, the motivation for it was to obtain the Riemann zeta function as partition function of a system. Somehow, therefore, the energy levels of the system maybe could perhaps just shed some insight on the Riemann zeta function. Now, it's a good idea, but it doesn't really yield. It hasn't yielded any insight, but it was picked up by Boston Con, this idea, and they said, well, the system is not interesting because there's no interaction between the primes. This is a system that is, the primes are decoupled from each other. So they came up with another system, and this is back in '95. This is how I got interested into this subject. And this is, again, it's a system of primons, and they're interacting. So how they interact? Well, through a Hecke algebra construction that I don't really have time to explain. Oops. I'm puzzled by this. Does it appear on your screen?
Yeah, you should be able to remove it.
Yeah, you should.
I can try.
Oops.
Clear all drawings. You see, I removed.
Oh, you did. Thank you.
Yeah.
Oh, okay. Okay, so there is a sister algebra called the Boston-Hecke algebra, which is a Hecke algebra or a Hecke sister algebra, and it has the dynamics. And it is possible to represent this sister algebra as a cross product. So this A here should really be CQ. It's a cross product of the sister algebra.
Is it obvious what is with L and R, all that stuff?
No, I will say okay. In a minute, but yeah, okay. Oh, thank you. So when you have a Hecke algebra, you start, when you want to construct a Hecke algebra, you start with a group. In this case, a semi-direct product of the rationals, multiplicative rationals, positive rationals acting on the rationals, and with a semi-group of integers. And this is what's called almost normal or a Hecke subgroup. And what that means is that the double cosets are unions of finitely many left cosets, and that's this number, how many. This is in the double coset of gamma. You have L of gamma left cosets and R of gamma right cosets. And if you take the quotient L over R and raise that to the IT, then it gives you the dynamics applied to the double coset of gamma. I really don't want to get into the details of Boston, but I want to say that there is a sister algebra, the Boston algebra constructed as a Hecke algebra, which is generated by some isometries μn, some unitaries ER. The isometries are indexed by multiplicative natural numbers. The unitaries are indexed by the additive group Q mod Z. These are the rational points in the circle. And the products are span a dense subalgebra. And the only reason I want to show you this slide, I don't want to get into Boston, is that in this case, the structure of equilibrium states is very interesting. And the reason for that is that for beta bigger than 1, if you compute the KM states and look at what the extremal KM states are, they're indexed by a very interesting group. So there is the oromorphism of Q mod Z, which is a group isomorphic to the Galois group of the maximal Lagrangian extension of the rationals. That group acts freely and transitively on extremal KMS states. We also have a formula for the KMS states, and we'll see a similar formula. I don't want to get into them. But I want to point out that there's a very different behavior in the region of divergence of the Riemann zeta function from the region of convergence. So for the convergence region, you have a multiplicity of extremal states. And for the divergence region, you have a unique KMS state. And this is interpreted as symmetry breaking in the sense that the unique state for high temperature, which is low beta because beta is the inverse temperature, the unique state for high temperature, when you cool down the system past the inverse temperature 1, you pass from a unique state that is symmetric with respect to this Galois group or oromorphism of Q mod Z to a free transitive action of the Galois group. And the implication is that by freezing this system from the unique symmetric state to a free transitive action on extremal states, you have discovered an action of automorphism of Q mod Z or the Galois group with the maximal Levinian extension. And potentially that can be if you go to infinite beta or absolute zero. There's hope that this gives you information about class field theory. So the only point I want to make is that as soon as there is some sort of interaction, and the interaction here is implemented by this Hecke algebra, then something very interesting happens in terms of the phase transition, which means the diversity of equilibrium states as beta tends to infinity.
Sorry, may I have a question?
Sure.
Do you know any examples in which also type 2 appears in a similar?
No, I don't know. I don't know phase transitions of type 2. I suppose that one could break them, but I don't know. I know type 1 and type 3.
And maybe follow-up question, this hyperfinite free one factor is also very, very common in those considerations. Do you know any examples when you get some other type 3 factors?
Yeah, there are 3 lambdas that appear. Yeah.
Ah,
Yeah.
okay.
Function fields.
Okay, thank you.
Yeah.
And I have a stupid question. When I look at this formula here, I see A, and there's no A on the right-hand side.
Yeah, okay, that's A is the reduced fraction for R.
Aha.
So sorry, I should have explained that. So R is equal to A over B in reduced terms. And you will also notice that on the left there is an A and on the right there is no A.
Mm-hmm.
And that in some sense is a symmetry. That state is symmetric, so A doesn't make any difference.
Mm-hmm.
It only depends on the denominator.
Okay.
So that's because the state is symmetric with respect to this Galois group. Okay. One quick introduction to another system. Oh, I wanted to say something. The Riemann gas is purely multiplicative. See, the only structure of numbers that is being used here is a multiplication. And multiplication is a commutative operation. So one doesn't expect or doesn't get anything very interesting from the Riemann gas because it is essentially classical, it's abelian, it's non-interacting. Here, Bose-Kohn consider the semi-direct product that it includes multiplication and addition. And it's essentially because of that, although multiplication is commutative and addition is commutative, when you put them together, you get a non-abelian group. And that's what makes this quantum system interesting, is the interaction between multiplication and addition. Now, there's another way of making multiplication and addition interact, and that's just plainly take the semigroup or the monoid Z with an action of m times. So you just take the positive, strictly positive integers acting by multiplication on Z with this operation.
Ah, this was in the abstract, I remember, yes.
So if you do the left regular representation of that monoid on its Hilbert space, and that means well, it's a left creation operator by now there's 2 parameters R and A, but it's the standard construction of a left regular C-star algebra. And if you now take mu sub A to be multiplication by A and U sub R be translation by R, then you have again a similar feature to Bose-Kohn, that the monomials mu A, U R, mu B star. This is some sort of weak order, weak as in W-I-C-K, weak order product that span a dense subalgebra. And they are analytic. It's easy to see that if you compute the dynamics on one of these guys, this A to the IT can be turned into A to the IZ and gives you an entire function. So this was, we started with Ian Rayburn in 2010, this system. And what we got is something that is slightly similar to Bose-Kohn, perhaps less interesting, but no KMS state. There's a shift in temperature. There's nothing happening between 0 and 1, no equilibrium. But between 1 and 2, this is a critical interval. There is a unique state, which is, we proved with Sergei that is type 3-1. And but above 2, so for between 2 and infinity, the simplex of chemistase is isomorphic to the Bauer simplex of probability measure. This means that the extremal points are indexed by the circle, by the points in the circle. So again, there is a phase transition of the type for high temperature, that means low beta, there's uniqueness, and for high beta, low temperature, there's a multiplicity of states. So again, I don't want to get into details for this system, but let me show you a picture of what it looks like from what we knew in 2010. So for this green, I'll have another semi-group, so I'll call them by color. For the green one, which is the multiplication, is on the right. The extremal chemistates are, if you index by measures on the circle, there's a constant simplex between 2 and infinity. And this constant simplex is the measures on the circle. So if you think of the extremal points, you just think of a circle. So there's a constant circle. And as it tends to 2, then all of them converge to 1 point. And between 1 and 2, there's unique equilibrium. So there's a unique equilibrium between 1 and 2. There's nothing below 1, unique between 1 and 2, in a circle for bigger than 2.
And what exactly do you mean by this notation? T or J?
It's some sort of a make up picture for what I would say the phase transition, which means on the axis here, on this real axis, the inverse temperature, and the section above a point is some sort of picture description of the simplex of KMS beta states. And I didn't want to draw a simplex, so I drew the extreme points. So on top of this value beta equal fixed beta bigger than 1, there is a simplex that corresponds to all probability measures on the circle. So I drew a circle, and those are the extremal points. That's perhaps, it's not standard, but hopefully it helps, intuitively helps understand the type of phase transition that we're facing for the system. Are there any other questions? Because I'm going to show you other diagrams like this, so if you want to ask me.
Adam, Tomek?
No, I think it's clear, at least for me.
Okay. And then include
Wait, there is one.
Okay.
You could go back to the previous slide for 1 second.
Oops.
Oh no, okay, I think I misread something, but it's okay. Thank you.
Okay, sure. And I also included
Can I ask the sorry, it's Ludwik Dabrowski. Can I ask for the Mathematica Physics for the first example? You said for beta greater than 1, so small temperatures you have unique. For beta smaller than 1, what happens in the first example?
In the first example?
Yes.
The first example was the matrix system.
Yes.
It's unique
Simple.
throughout. There is a unique state for all betas.
Okay, thank you.
I'll show you. Okay, here's the picture for that one.
Wow.
So here's a list of a bunch of systems, and I'll say a bunch of things about them. For general culture, I won't be able to get into any depth because I want to get to the point where I talk about the research that motivates the talk. But the question about the first example is explained here. There is a type 1. This is blue. Blue means cold and means type 1. So for the matrix system, there's a unique equilibrium state. This blue line is at 1 point for each beta. So there's not much to it. For the Riemann gas, so I would say there's no phase transition there because the KMS simplex remains the same at all betas. For the Riemann gas, or triplet system for n cross, there is uniqueness. That was that tensor product of unique states. But there is something that changes at 1 because we pass from convergence of Riemann zeta to divergence of Riemann zeta. And divergence of Riemann zeta, the state has to be represented using some sort of Euler product. And the type changes. So for beta bigger than 1, there's a unique state of type 1. For beta smaller than 1, there is a unique state of type 3-1. So that change I represent by changing the color of the line here. So it's a unique state, so in the sense of the simplex, it's the same simplex, but the type of the point that appears. So this is 3, this red one here is 3-1, this blue one here is 1 infinity. So we can say there's a phase transition because there is a change in the nature of the equilibrium, although there's still uniqueness of equilibrium. So for the Bose-Kohn system that I mentioned, there's a bunch of states, so the KMS simplex is indexed by the Galois group with the maximal abelian extension at each point. And when the temperature passes through 1, they all coalesce into one single equilibrium state, which is type 3.1. So there's unique for type 3.1 between 0 and 1, and then a multitude of states for beta bigger than 1. And there is a whole interesting area of research, which is how to, how to generalize this. This is related to the last one in the list here, to get some idea of, or some insight on class field theory by analyzing the action of this Galois group on the states themselves, the values of the states. So it's a whole area that was sparked by this construction of Bose-Kohn. The green system that I just showed you for the Toeplitz algebra, this should be a Z here, oops. Should be a Z there. It has no equilibrium state between 0 and 1, a unique type 3.1 between 1 and 2, and then a circle at each beta between 2 and infinity. So the phase diagram in some sense is similar to that one, but the symmetries, instead of being symmetries, Galois symmetries, they are just circular symmetries. And this has to do with something that Sergei studied later and led to a significant advancement understanding the KMS states of group with isotropy. This was one example that motivated.
Mm-hmm.
In work with Kunz and Denninger, I later studied a generalization of this green system where we substitute n by the integers in a number field, an algebraic number field. If you take the ring of integers in an algebraic number field, then you can do the same semi-direct product construction. And what we found is similar. There's nothing between 0 and 1. There's a single type 3.1 state between 1 and 2. But for beta bigger than 2, the problem of computing the KMS simplex at each beta became, okay, we stated this, they're indexed by extremal invariant traces of the action of the units in the number field on the ideals. But, and that's fine, but if you go deeper than that and try to understand because you understand what ideals look like, they're just Z to the D modules. And the units are, again, free abelian times finite abelian group. If you start looking at those actions and try to decide what are the extremal traces, then you come up with a question of invariant measures under toral automorphisms, linear toral automorphisms, which is extremely interesting, and it's a generalization both in terms of dimension and in terms of rank of something called the Furstenberg's question or Furstenberg's conjecture. So we don't really know in general what these extremal trace spaces are, because we don't know the answer to these generalized Furstenberg conjectures. We can compute the measures that are supported in finite orbits of the action of units on tori, and we can also compute a hard measure of the torus. But we don't know if there is a singular measure. It is not known if there's a singular measure that is invariant, which is that's a generalized Furstenberg. So by looking, in some sense, by following our nose and trying to compute equilibrium for a system for the ring of integers, we fall right into a very interesting area of research, which is this generalized Furstenberg conjecture. And one more thing, the generalization of the Bose-Kohn, it has been done by many people, but in particular, with Sergei and Mark Trifkovich, we obtained a Hecke algebra generalization that has a similar feature. The unique equilibrium up to 1, similar feature to Bose-Kohn, unique equilibrium up to 1, and then a Galois symmetry of the maximal abelian extension from 1 to infinity. So
And what is the meaning of this plus next to Hecke?
this plus, okay, yeah, good eye. So it's a Hecke system in which the multiplication is not just by non-zero integers, but it's by totally positive non-zero integers. So totally positive non-zero algebraic integers are the ones that in every embedding, in every real embedding, they embed as positive numbers. And that's a technicality that has to do with how to represent class field theory without using infinite places, right? There is a limitation in the systems that we consider, in that they only consider the Adels, the finite Adels, or they yield the finite Adels. So there is a bit of a problem in generating the full Galois group of the maximal abelian extension. But if you restrict multiplications to totally positive elements, then there's a trick that shows you that the Galois group of the maximal abelian extension is what's acting on the states. So the plus indicates that multiplication is by positive. It's already happening here. I mean, we always take the natural numbers and multiply. We're not using -1. So this positivity is being implicitly assumed in the other models. It's not an essential feature, actually. It is in this case to get the right group. And if you don't get the right group, you get a very similar group of symmetries, I mean. Okay, so this is a zoo of various phase transitions. And what I want you to take away from this is that for high temperature, that is for small beta, there's always one. You know, all of them have one. And the idea of that is that although these systems are not physical, there is a physicality to them in the sense that when you heat them up very, very hot, they melt in a homogeneous phase. They don't have different plasmas. There's only one single, completely chaotic state that represents the system at high temperature. I'm going to step out to plug in this laptop because I'm running out of battery in a second.
Okay.
Okay, so here comes the thing that we actually did study, which is the monoid, and it's a similar monoid, but the multiplication is on the other side. What that means is that when you multiply A in a multiplicative integer, non-zero, positive integer, and R, so this A is in N, and this R is in Z. When you multiply 2, you multiply them like this. And it's impossible to remember, so I take this slide, you will forget, but think of it this way. The blue system has a matrix representation that is upper triangular and has a multiplicative at the bottom. It's exactly like Boscon system. When they represent them, their system with their elements by matrices, this is the choice. And the relation to the other one is that it's the opposite. So the blue n cross times z is equal to the opposite of the green z times n cross. They go together. And the opposite is the same as A inverse, as submonoids of the group that contains them both. And you would think that as opposites, they have the same properties because you just have an anti-isomorphism, and that's true. But there's one difference between a semigroup monoid and its opposite. If we're going to choose to represent things by left creation operators, then things become different for these two. And the way it shows here is that if you look at what's called a principal right ideal, which is a set of right multiples of an element. So here's the element, I multiply by all the multiples that I can put on the right, and this is what I get. So I get multiples of A for the multiplicative part, and XR, so this R is multiplied by the X, and you add Y. But the point is that this Y is free, so this is taking all of Z. There's no restriction on this result here because Y is ranging over the whole Z. That's different. If you do the same thing for the green one, then there's a restriction on the right-hand side. So, and the way that shows is that if you take the intersection of two of those, here's the right multiples of AR, and here are the right multiples of BS. What you get when you take the intersection is, well, you have to be multiples of A and multiples of B, so it'll be multiples of the least common multiple of AB. And then you can put anything you want here. This 0 is just convenient, but you can put any number because it doesn't matter. The right multiples of this are independent of what you put here. So the point is that the intersection of right multiples, first of all, is non-empty and is the right multiples of another element, in fact, of several other elements. That's called the right LCM property. The right LCM property holds for this blue n times cross z, but it doesn't hold for the z times cross n times. So we thought at the beginning that we would get, this is something we started with, we initiated with Rayburn, the green one, and then 10 years later we thought, what about the left one? What about the other, the opposite? We thought we were going to get a similar result. But when you compare the blue and the green, you see that some things are different. Like I said, this is right reversible. This means that the right multiples and the always intersect. And it's also another way of saying the same thing is that if you do the right quotients of the monoid times its inverse, you get a group. This is not always true that if you do a monoid times the inverses, you generate a group. But in this case, you do get a group. It's not true for the green one. This one is, of course, left reversible, but it's not right reversible. If you look at the left regular C-star algebra, which is generated by the left regular representation on L2 of the semigroup, the left regular C-star algebra has a distinguished quotient called the boundary quotient. And for the blue semigroup, it is a group algebra of Q acting on Q multiplicative acting on Q. And this semi-direct product has lots of one-dimensional quotients. It's very far from simple. But if you do the boundary quotient of the other one, the green one, then that was a motivation that moved Ian and I to study this. The boundary quotient of this one is Kunz's Qn, which was introduced the early 2000s. And that...
Yeah, but wait, what do you mean by this Qn? Do you mean like O infinity?
No, it's similar to O infinity. It's like a bunch of ONs, but no, it is what you get if you do additional multiplication on n. So,
But it's better if you write on the screen.
we're going to have a hard time writing on the screen. So I think you have to do this. So,
But we cannot see anything anyway, so it's invisible. I mean, you are small.
You're not seeing me?
When you see, yeah, but when you share screen, even on a big laptop, you are 2 centimeters by 3 centimeters big. So when you write on the blackboard, it's like 2 millimeters.
I see. Okay, so we'll have to do without. I don't have a way to write on the screen. So let me say that Kunz's Qn is what you get if you take L2 of Z.
Okay.
And put a translation operator by one. And you put a multiplication operator by a positive integer. And you generate a C-star algebra with that.
Okay.
And that's Qn. So it's the left regular representation of this monoid on n, on Z. So that's the boundary quotient, that's Qn. Whereas the C-star of Z mod n is the left regular representation on itself of the self of Z mod of Z times n.
Wait, sorry. And the multiplication operator is by a fixed integer or by the integer that corresponds to the entry of the vector it is applied on?
Sorry, I didn't quite catch that. Can you ask me again?
Yeah, like what is the nature of the multiplication operator you mentioned? Is it by
take a standard basis vector delta sub n, and the multiplication m sub a just sends delta sub n to delta an.
M sub a
So you just act on the basis vectors.
Right,
Yeah.
yes, okay, of course, thank you.
And so you act by multiplication and by translation on the basis vector. The difference between Qn and C star of Z times n is the Hilbert space. In Qn, you use L2 of Z, and in C star of Z times n, you use L2 of Z times n. And because you use a bigger Hilbert space, your C star algebra is bigger, but the other one is a quotient of it. And it's a standard quotient. It's a quotient that appears, it can be characterized in many ways, and they're all equivalent. It's a smaller, in this case, it's the smallest non-trivial quotient, but it's also the smaller, it corresponds to the quotient by the largest invariant ideal. It corresponds to the C star envelope of the tensor algebra. It corresponds to, so there's a distinguished quotient that wants to appear no matter what you do, and it is isomorphic to Kunz's Qn. But the point
And what is the case here of this Kunz's Qn? I'm really puzzled by this.
Wait. So it's simple and purely infinite.
Yeah.
So the boundary quotient, which is a standard construction on a C star algebra, coming from a semigroup, are very different. One is non-simple, the other one is purely infinite simple. But if you look at the reduced C star algebras of the blue one and the green one, they're KK equivalent to C star of the integers. And because of that, it's something that was proved by Kunz, Lee, and Echterhoff. Because of that, they have the same K theory. So these C star algebras are very different. They have, different come from different semigroups. They have different boundary quotients, but K theory does not distinguish them. And the reason it does not distinguish them is that it's this C star of Z that controls both. Okay.
Yeah, but this is for this one. And how about this Kunz's Qn? What's the K theory?
Oh, I don't know. I think yeah, I don't want to venture a guess. I don't know. I mean, I think it's known.
Okay.
But,
Okay.
yeah.
Okay.
So if you now compare the K state space of the two C star algebras, on the one hand, you get similarities for low temperature. Both are indexed. The extremal points are indexed by the circle. And in some sense, that can be explained using some recent work of Sergei and Makoto, Yamashita, and I. They both have some sort of bimodule algebra structure on which the coefficient algebra is C star Z. The coefficient algebra is the crystal, what we call the crystal. So because the crystal is the same, then our crystallization theory predicts that the K states are going to have the same structure. So this is an example. In fact, it's a motivating example. But if you now move to high temperature, this is where the surprise came. We have computed, as we saw in the diagram, the green one, the Z times n, it has a unique equilibrium state for the critical interval between 1 and 2. And what we will see, and this is what I will start talking very soon, is that this new example, the blue one, n times Z, it has infinitely many extremal states for beta between 0 and 1. Don't worry too much about the critical interval here being 1, 2, or 0, 1. There is a shift in inverse temperatures that has to do with the structure of the semigroup, which has to do with the growth of the semigroup, which has to do with the convergence region of the partition function. So it gets shifted, but this 0, 1 here corresponds to 1, 2 there. And the point is not so much that the interval is different, but that there is a very important change from uniqueness to infinite limit.
And why? Sorry, can you go back, please? So here this interval is closed 1 and 2, and here it's open on the left.
Well, yeah, we can close it, but then the reason I kept it open at 0 here is that for 0 there's 2, so it's not infinite. There's still multiple, but there are two states. So. So if I hadn't said infinite by multiple, then I could have included the 0. But we know what happens at 0. It's just not infinite.
Okay.
Yeah, I'll show you a picture in a minute.
Okay, okay. Thanks.
So we started this a while back with Astrid and Huff and Ian Rayburn. And we studied the phase transition for beta bigger than 1. We first studied the C-star algebra. Let me now we're going to be a bit more specific, and let me tell you what the C-star algebra is. So it's the left regular C-star algebra of the semigroup n times z, and it's generated by isometries. And here's the isometry L of the element AM acting on a standard basis vector delta Bn. And what it does is it just multiplies as in the monoid for the subindices. So it's AB and BMN. And that's the orthonormal basis of the L2 of n cross times z. If you want to understand, it's better to have a few generators that generate the whole thing. And it's better to separate multiplication and addition. So you take U to be the add plus 1. So this L11 means multiply times 1, which is do nothing, and add 1. So U is translation by 1 in this semigroup. And VA is multiplication by A. So add nothing, multiply by A. So then LAM is VA U to the M. So that's the C-star algebra generated by the LAMs is going to be the same C-star algebra generated by the U and the VAs. And the U and the VAs satisfy the following properties. VA is an isometry. That has to do with this formula here and the fact that the semigroup is cancelative. And U is a unitary. Well, if you look at this semigroup, the element 1, 1 is invertible. So when you represent it as an isometry, you get an invertible isometry. So U star U is equal to U star equal to 1. So the VAs are isometries, the U is a unitary. And the way they multiply, well, they multiply like the semi-direct product, like the semi-direct product rule. If you add 1 and multiply by A, it's the same as multiply by A and adding A. So that's the commutativity of addition and multiplication. But the multiplications, of course, behave like multiplication. And there is this property here that if you have relatively prime, the multiplication operators not just commute, but star commute. One commutes with the adjoint of the other. This is a feature that is also seen already in the Boscon system, in the Riemann gas. And this one is double parenthesis here because although it's an interesting equation that is necessary for many formulas, it is in fact a consequence of the other one. So 0, 1, 2, 3 imply 4. And the fact is that this regular C-star algebra defined concretely as operators on L2 is in fact universal with respect to the relations 1, 2, 3, 0, 1, 2, 3. You can put 4 if you want, but you don't need to because it's a consequence. And again, as in other examples, because of this commutation, you can have weak ordering. If you look at all these relations, you see that if there is an adjoint to the left of another element, you can pass it to the right. So in the case of an isometry, it's trivial because you get the identity. But here, if you have a and B, then you can write B and A. And here you have a star and a U, then it's a U and a star. So you can weak order by putting all the annihilation operators first and then all the creation operators last. And what you get is these monomials here, VA, U to the K, VA, B star. And where A and B are multiplicative and K is additive. And they are closed on the multiplication because of this weak ordering, and they're closed at the adjoint. So if you just take the linear span, you get a dense subalgebra. What I'm saying is that these monomials control what happens for the C-star, what happens in the C-star algebra. And if you now define a time evolution on this T here is from it's just notation. This is C-star. This should really be C-star. This less regular C-star algebra, sometimes we call it Teplitz algebra, so that's why the T, but it's the same as C-star. So the dynamics of this C-star of n times z is defined by taking a Hamiltonian, and here I have the right formula. H delta AR is log A of delta AR. So you put energy levels logarithm of the multiplicative part. And for a real number, sigma t of the generating isometry LAR is conjugation by this exponential e to the ith, e to the minus ith. So it's implemented in the left regular representation. Is implemented by this unitary group whose infinitesimal generator is this Hamiltonian. That's implemented spatially, but you can also, since we have this presentation here, you can also decree that sigma t is going to fix u, and sigma t is going to move a to the it VA. And the fact is that if VA is a semigroup isometrist, then so is a to the it VA. And if VA satisfies the presentation, then so do a to the it VA. It's because they're scalars, and either they commute with everything or they cancel themselves. So for the generating elements VA u to the k VB star, the dynamics just takes the A and the B, forgets the k because u is fixed, and takes a over b to the it times the same element. So these monomials that span a dense subalgebra, they're eigenvalues for the dynamics and the eigenvectors for the dynamics, and the eigenvalue is this ratio of a over b to the it. And they are, of course, analytic, because where you see this t, you can put a z and you get an entire function. So to study KMS states, it's enough to focus on these monomials because they're analytic and they generate a dense subalgebra. And if you just focus on U, it's fixed, so it's contained in the fixed point algebra. And the C-star algebra of U, this is a universal unitary. So the C-star algebra generated by U inside this left regular C-star algebra of n cross Z. This is isomorphic to the continuous functions on the circle. Okay, so now we have the algebra either by left regular or by presentation, and we have the dynamics either by spatial implementation or using the presentation. And the first theorem that we proved with the first study of KMS states was for beta bigger than 1, so this is the cold state, so for beta between 1 and infinity. We found that the KMS states are parameterized by probability measures in the circle. This is not surprising because this is sort of predicted by this crystallization. And the correspondence is you take a measure, you're going to get a KMS state for a fixed beta. And what you do with the measure is you take the powers of the unitary, you add them with coefficient c to the minus beta, and the a and the b are, okay, so the a and the b are only appear in this coefficient here. And the reason is that the KMS condition tells you can put this a over here and affect it with a factor a to the minus beta. And if you do it twice, you realize that a has to be equal to b. So a has to be equal to b, and what gives you different values is this n here. So you take u to the n raised to the power c, coefficient c to minus beta, add up, and then you normalize by zeta function of beta, which is the sum of this c to the minus beta. So we established an affine isomorphism between probability measures on the circle and KMS beta states at a fixed beta bigger than 1. And the idea of the proof is what I was just saying over there. You just move this over there, realize that a has to be equal to b, and what you have is a factor and then field restricted to the powers of u. So the KMS state has come from states of C star of u. It's just that restriction to u that controls the KMS state. But the trouble is that not all restrictions are, not all probability arises as restrictions, only some of them. And the problem is to determine which ones. And with Astrid and Ian, what we did is realize that these ones that appear in our formula are all. So all KMS states arise as from the restrictions that are represented in this way. So if you have the restriction of a KMS state, then there is a measure that gives you that restriction via this formula. So that there's a computation of KMS states for high temperature, for high beta, that relies on the conversions of the zeta function. So I'm not saying it was easy, but it was the same kind of argument that we had seen up to then with some variation. But it was not surprising because we got a circular symmetry. We were kind of expecting a circular symmetry. And then we said, well, what happens at 1? And then we took some limits. And when we took some limits, it was very strange because depending on how we took a KMS state converging for beta, we could trace some families of KMS states for different betas. And if we choose a certain family, we got a limit. And then we chose another one, we got a different limit. And we chose the average of everything, so it's Lebesgue measure on the circle, and we got a different limit. And then we realized we don't understand what's going on. There's a multiplicity at 1 already, and we computed actually 3. There's a multiplicity at 1 that we have never seen before, and we don't have the techniques to approach it. We can play with limits, and we realized that we could keep taking limits and rig them so that we got different states at 1, but we didn't have a theory where we could actually say, well, we're going to compute them all. So we kind of put it aside. We finished the paper. The paper states essentially this picture. It says that for beta bigger than 1, there's a circle, the Bauer simplex of the circle, meaning extremal KMS state for each point in the circle. And we gave as example 3 different ones and how to obtain them by taking limits. And we left it at that. So that was a paper that appeared in the New Zealand Journal of Mathematics in 2021. So then I said, well, I want to know what happens. So I proposed the question to Tyler Schultz, and we sat and we looked at the structure of the C-star algebra. We looked at the spectrum of the diagonal, trying to understand what was going on, because from experience, we know that what happens depends on the orbit structure. So we started looking at that. And we proved the following thing. Remember that from the study that we had done for temperature bigger than 1, we needed to know which restrictions appear. The KMS state is determined by its restriction to the C-star algebra generated by U. We wanted to know which restrictions appear, so which states appear as restrictions. And what we came up with is the state of C-star of U, which is a circle, extends to a state by this formula if beta satisfies a property we call beta subconformal, which appears already in other ways in studies that have been done for right LCM semigroups. And what beta subconformal means is that for each n, the measure that corresponds to the state satisfies this positivity here. So if you wrap around the circle, so this measure, you integrate against the measure, but not the function, but the wraparound function, and you take d to the minus beta, which is how many times you wrap around, you divide, and this mu is the Möbius formula, the Möbius function, which tells you you only take d that has not repeated, doesn't have repeated primes. So the Möbius function counts how many different primes there are in the factorization of d, and puts 0 if there are repeated primes, and puts -1 if there is an odd number of primes, and puts +1 if it's an even number of primes. So this is eliminating repetition of primes. So if you do that formula, that we call beta subconformality for reasons that may not be clear, then if you have this positivity, you can extend the state determined by nu to a state of the C-star algebra. And as soon as you extend to a state, this formula tells you there's going to be a KMS state. So the issue is not the KMS condition, but the positivity of the extension. So we characterize that. That was our first result. We said, well, this is a subconformality that ensures positive extension and therefore KMS state. And then we started developing ways of computing beta subconformal measures. So the problem becomes now, what are the measures on the circle that satisfy this positivity? And if you want to understand what the measures are that satisfy the positivity, well, it pays to go back and see what Astrid and Höfvi and Raver and I had done for the convergence region, for beta bigger than 1. We had actually solved the subconformality question by giving an explicit formula. So beta is subconformal if it is obtained as this series of mu of the powers of u to the n times c to the minus beta. So these are the Fourier coefficients of the measure here. This is the measuring value that essentially is z to the n. So the Fourier coefficients have to come, have to come from a measure mu. But obviously this doesn't work for beta between 0 and 1 because the zeta function diverges, so you can't divide by the zeta function. So we need a different approach. But the idea remains that you actually have to solve this. And the different approach is to think the zeta function also has a Euler product. And if you interpret what needs to happen for the Euler product, it is written here, beta subconformality corresponds to the product of overall prime that divide n without repetition. So prime divides n, you put it here, of 1 minus p to the minus beta, and then this WP star. This WP star is the wraparound map. Here's the wraparound map on the circle. Here's what it does to measures. So it's the adjoint map on measures. So if you take this product and apply it to a measure, you get a positive measure, then you have beta subconformal. So beta subconformality now is a positivity in kind of an Euler product, but it's a finite Euler product. It's something that depends on the device, the prime divisors of n. So this is, in some sense, an Euler Möbius inversion formula from this to that. And there are technicalities, but the point is that we were able to exploit this Euler formula of positivity of the Euler product. And for the system that we're studying. And the first observation is this beta subconformality respects the atomic non-atomic decomposition. This means that if you have a beta subconformal measure, the atomic part is beta subconformal, and the non-atomic part is beta subconformal. So you can split the problem into two. And then you look at the atomic part, and you prove directly that the atomic beta subconformal measures have to be supported on roots of unity. Otherwise, they cannot be probability measures. So if they're probability measures, they have to be supported on roots of unity. And then we can use this Euler product because it so happened that the extremal ones, they have to be supported on finitely many roots of unity. So we can actually use the inverses of this operator for n. You don't have to go to infinity. This n can be chosen large enough but fixed. And these operators have inverses. So when you do the inverse, you can exploit this. You take the inverse of a measure, and you get a beta subconformal measure. Now that leaves us with the non-atomic part, and that's difficult because to show that Lebesgue measure, which we knew from the work with Astrid and Ian, was beta subconformal, there's only to show that the Lebesgue measure is the only non-atomic one. We need to prove some subtle, maybe perhaps not deep, but rather subtle asymptotics of the distribution of primes. And what it comes down to is a modification of Wiener's lemma. Wiener's lemma says that the coefficients of a probability measure on the circle tend to 0 as a zero sum, and we have to have like a multiplicative version of that. So if you take a subset of integers that have natural density 0, that means that if you take the initial segment of integers and the proportion of elements of J in that initial segment tends to 0. Then it also goes sort of multiplicatively to 0 in this sense here. So here you take the first p prime, the first n primes, and here you take the semigroup generated by the first n primes. So the elements of J that are factorizable in the first n primes, you add them, you have the 1 over m's, and that tends to 0, provided that J has natural density 0. And then once you have this asymptotics for this sort of multiplicative averages, then we use it to prove some sort of ergodicity of a dilation, very similar to what Sergei has done for the Bose-Kohn system. So we prove that any non-atomic beta circumformal measure has to be ergodic, so it has to be unique. And since we already have the Lebesgue measure as an example, then the Lebesgue measure is the only one. So this is the idea of the proof. There are technicalities here that I'm completely not talking about, but the ideas are clear. The ideas are to use this Euler product for operators on measures and exploit the fact that you can separate the atomic case and the non-atomic case. They both require very different techniques. But anyway, after we do that, then we can actually compute it. And what we found is that for each n, there is a beta circumformal probability measure given by this. So this is explicitly the measure. At a point z, the measure gives a number written here if z is an nth root of unity and 0 otherwise. So it's concentrated on the nth root of unities, but it gives values according to the order of the root of unity, where this phi is the Euler function, that is the size of the multiplicative group of z mod d. So this is the Euler number, the number of how many numbers are relative prime to d between 1 and d. And this is some sort of thermodynamical version of the same function where we affect the factors by beta. So d instead of d to the b instead of p to the minus 1, p to the minus beta. So we call it thermodynamical Euler function. And for infinity, you put lambda, the Lebesgue measure. And that's also subconformal. So here are the atomic ones. They're supported in roots of unity. And here's the Lebesgue measure. And
sorry, could you explain again this z mod dz star? This is the counting of what?
so if you take a number d and take integers modulo d, that's a ring. And as a ring, it has a unit.
Yes.
Invertible, multiplicatively invertible elements. And that's the size of the group of units.
Okay.
So if you think of arithmetic modulo d, what I'm talking about is the numbers that are relatively prime to d.
Okay, yeah.
To be invertible in that ring, you have to be relatively prime to d. And the size of that group of units, of invertibles mod d, is the Euler number.
Okay.
It has other definitions too, but that's perhaps the quickest one. So the theorem, the content is that this restriction map that takes a state and restricts to a measure on the circle establishes a weak star homeomorphism between the extremal KMS beta states here and the set of measures listed here and there, which is as a topological space is the one-point compactification of the multiplicative integers. So extremal KMS states corresponds to extremal beta circumformal probability measures, which are listed. And now we have a complete list. There are these ones that are supported in roots of unity, and there is Lebesgue measure. So that's our classification. And if you now pass it to the monomials, and this is in some senses, you look at the state, the Fourier transform, or you look at the values of the KMS state on the spanning monomials, then there is a formula here where instead of the Euler product, you get this. I don't think this is going to help us much. But the point is that we can parameterize and we can give formulas for it.
That's quite recent, 2025.
Sorry?
It's quite recent, this theorem, 2025.
Yeah, we put it on the archive yesterday.
So that's very recent. Okay.
So here's the picture. I wanted to show you this picture. So here's how we completed, Tyler and I completed the picture that we had done with Ian and Astrid. Before we were seeing a circle, and the circle is, you see a circle, you see a rotationally invariant picture. But when you look at the phase transition as you approach 1, this circle, it makes a difference. This circle is composed of irrational points and rational points. Mm-hmm. And there is an issue of the parameterization, and I'm not being completely honest, but this is supposed to be the circle of beta subconformal measures. As you're approaching 1, the purple points, which are the irrational points, they are extremal. Each one of them is an extremal K-ms beta state. They all collapse into Lebesgue measure. Uh-huh. Think of that measure being spread on the orbit of an irrational point, which is dense and somehow generates Lebesgue measure. So all the purple points, they coalesce into Lebesgue measure at 1. But the orange points, these are the rational points, they have an order. When you have a rational point on the circle, there's a denominator there. It's a root of unity of a certain degree, of a certain index. And they collapse, but they collapse in order. So the root of unity of order 1 becomes one state at 1. The primitive root of unity of order 2, which is -1, gives you another one. Here are the 2 primitive of order 3. They go to another one. Here are the 2 primitive of order 4. Here are the 4 primitive of order 5. So they collapse according to primitive order. And they collapse into a distinct state. So this collapsing doesn't mix order. It preserves the order of the roots of unity. But it collapses all the roots of unity of the same order. And that collapse remains. So through the interval 0, 1, these are different K-ms states. These are the psi beta n that I had in the previous slide. There's 1 for each n. And they come from the collapsing or the coalescing of the roots of unity of a given order. And we proved that they are type 3-1. I may be able to say a little bit about that, maybe not. But the point is that only at 0 they all coalesce into 1. This is the evaluation at the identity. A Lebesgue measure preserves itself up to 1. So at 0 there's 2 K-ms 0 states or invariant trace. Okay. So that's how we completed the picture, and the theorem essentially says what the picture says.
But do I understand correctly that at 0 everything collapses to this delta 1?
Everything that comes from an atomic beta subconformal measure collapses to delta 1.
Okay.
But Lebesgue measure does not. So you get 2 distinct states even at 0, two invariant traces at 0. Mm-hmm. So in the last minute, let me mention that there is a connection to Bose-Cohn's phase transition. If you look at the presentation of the C-structure of the monoid n times z, here are the relations. If you look at the Bose-Cohn algebra, here is the presentation. And they're lined up, they are the same. And this one here is not here, but you can get it from the unitaries. So in other words, there is a homomorphism from the template system to the Bose-Cohn system, and in which the isometries correspond, multiplicative isometries correspond to the multiplicative isometries, and the translation by 1 corresponds to, now you have to fix and choose translation by what. So you fix a rational, and you send translation by 1 to translation by that rational. So for each rational, there is a homomorphism. Mm-hmm. And that gives you a map from the template system to the Bose-Cohn system. It's associated with each rational. And it's compatible with the quotient of the template system, which is a finite system. And this finite system embeds here. So the diagram commutes. So as a result, we see that there are the Tople system has symmetries by endomorphisms, which translate to Galois symmetries of this finite system here. It's not finite, the additive part is finite. And they correspond to the Galois symmetries of CQ. So what we didn't see before, which are Galois symmetries here, there was an obstruction because you have addition and that breaks the Galois symmetry. Now can be seen through partial Galois symmetries of quotients, which are related to the Boscon C-star algebra. And that is to us, that is, okay, I think we've barely scratched the surface here, but I think we're using it for two things. One, to establish the connection and symmetry. These are symmetries by endomorphisms. But also, because and there's symmetry breaking when you pass to low temperature. But the key thing is that if you want to study the type, you can use this embedding of a quotient into the Boscon algebra to import the type of the Boscon algebra for the critical interval into the type of the Tople system. So that's how we know that they are type 3-1. We map a quotient into the Boscon algebra, and the fixed point algebra for the symmetries. In fact, it is in the Riemann gases, not even the Boscon algebra. Okay, I think I've run out of time. I never thought it was possible to run out of time. Thank you very much. I will stop here.
Muchas gracias.
Placer.
Pregunta?
This is just a bit more for us.
Giuseppe? No.
I have a very general question.
Yeah, just make sure that you speak to the microphone.
Yeah, I can't hear very well.
Yeah.
Hi, Marcelo. Thank you for your presentation. I was wondering if the fact that the semi-group you were working with is reversible, did it play any role in the proofs of the theorems you were showing to us?
Yes, very much. Let me close this window because it's very noisy here now. The fact that it's reversible is crucial when we try to prove I mentioned the uniqueness of Lebesgue measure as the unique beta conformal. The proof of that is follows along the lines of what Sergei did for Boscon system, and it was based on a dilation theorem that I proved about the Boscon system, and that dilation relies on the right reversibility. So at some point you want to use the group von Neumann algebra construction, and so you need a group actance. You need to pass from the semi-group to a group, and the way to pass to do that is through a dilation. So it is important that the semi-group is right reversible. For a right reversible, there is a dilation of the system, and that dilation, so there's a unique extension of a KMS beta state to some sort of locally finite KMS weight on the dilated system, and it is for that locally finite KMS weight that we prove uniqueness or ergodicity. So it plays a role. It wasn't not in the statements, but in the proof of uniqueness for the non-atomic beta subconformal.
Do you think that the results could be pushed to general reversible semigroups, or it is also very specific to that similar product?
I think there is a lot more to say about general reversible semigroups, but you have to be careful that some of the things depend on having this weak ordering. These monomials that generate dense star subalgebra of analytic elements, and in a general reversible semigroup, there is such a representation, but it's a bit different. So I would even the formulation of the results would have to change, but I'm sure something can be said.
Thank you.
Okay, anybody else?
I have a question, but first, could you go back to the slide that mentions, well, there was a slide that said supercritical something on the title, and right, so the slide just before this one. Okay. Great. So what you obtain here by the end of the slide is the anomorphism in the Wistar topology between the extremal KMS beta states
Mhm.
and beta subconformal probability measures on the torus.
Sorry, I didn't catch that last thing. Would you ask me again?
Right. So you obtain this homomorphism between the extremal KMS beta states, right?
Yeah.
And the extremal beta subconformal probability measures.
Yeah.
Okay? Right. So is this homeomorphism some sort of restriction of another homeomorphism? Is there some perhaps like bigger space of states that you also studied? It's really interesting. Something, for example, that is homomorphic to the whole torus or something like that.
No, I'm not sure. Okay. Let me explain why, at which level I'm talking here. Because I know these are Bauer simplices, it is enough to tell you what the topological space is. So that's why I'm talking about homeomorphisms. I could also have phrased this by saying that the KMS beta state K beta are affinely homeomorphic to the set of all beta subconformal probability measures. So there is an affine isomorphism of simplices. I'm not sure if that's what you're asking. It's an affine isomorphism of simplices.
Right. No, but I was
You're asking me something else. You're asking me about other states that are not these extremal KMS beta states.
right. So I'm interested in if you know anything about the topology of some sort of related states or something like that. Because I'm thinking maybe you use some sort of extension of the homomorphism to prove the homomorphism. Otherwise, how did you prove it? I'm interested like in this part.
Yeah. No, I off the top of my head I couldn't comment on that, but this is an interesting question. I mean, it's been perhaps not addressed in what we've done, but we're feeling more and more that these diagrams that I've been drawing are really interesting. There's this geometry, not just topology, but there's actual geometry in these diagrams, and it seems worth exploring. But we're only looking at the KMS states. We are not really moving outside into the state spaces of these C-star algebras. Having said that, from the KMS states of an algebra, sometimes you get all states of another algebra or all traces of another algebra. So
yeah.
Okay. But I think I understand what you're asking me. Whether we can establish some topological picture of a sector of the state space, model it with something.
That is exactly what I was pointing towards.
Yeah,
yes.
yeah. I don't think we have anything to say that is not just for KMS states.
Okay, perfect. Thank you.
Tomek? But it helps if you unmute yourself.
Good.
Okay, so let me say sorry about my naive question. Sometimes you are dividing by the zeta function, Riemann zeta. So the following question arises: what about zeros of zeta function? What is happening near these zeros?
Yeah. The study of phase transitions doesn't really shed light on that. The issues that arise from here are related to the pole at one, so in some sense they're very naive. they're related to the pole at one, analytic continuation around the pole at one, but they do not address the critical line for zeta. This is not within the realm of the study of KMA states. However, there is work of Alencon and also of Ralph Mayer, who have pursued questions, that kind of question, with a construction that is somehow inspired by this study of KMA states and phase transitions, but it goes beyond it. It is really a different construction. So the idea is that to construct ultimately a space on which there is an operator whose spectrum has to do with the zeros of zeta, but it's not part of the.
So the fact that you are interested in entirety of this doesn't help to in answering this question. What is happening with these KMA states around in the vicinities of zeros?
We don't know. What we know is
it at least meromorphic?
Okay, let me think a little bit. There is an extension, but there's an extension beyond like around the poles. It's not. It's not an extension that has to do with the zero of zeta. So maybe I shouldn't say anything because I don't have an answer for your question. So I really don't know.
Okay, thank you.
Anybody else? I don't see any raised hands. So in this case, let us gracias our speaker again. Thank you so much.
Thank you.
Let me stop recording.